Welcome to Engineering Mechanics, Chapter 2, Statics of a Particle. Today we're going to introduce the concepts of forces and vectors. We're going to discuss vector math. We're going to discuss vector components. To do that, we're going to talk about the law of sine and the law of cosine, and we're going to talk about vector decomposition. We're going to introduce the concept of equilibrium and free body diagrams. The free body diagrams are a huge part of this class and will be extremely important throughout the semester. And after we do all that, we're going to expand the discussion into the third dimension. So we're going to look at the following things. We're going to look at the effect of replacing multiple forces on a particle with a single resultant force. We're going to look at the relations between forces acting on a particle that is in a state of equilibrium. And we're going to use these concepts on anything where the size and the shape of the body is insignificant relative to what we're looking at. Again, this is one of those assumptions that you might assume, you might think is too constraining, too limiting. But in reality, this is a useful thing. Consider a rocket. A rocket obviously is not a small object, right? And so when you think of the size of the rocket relative to what we're looking at, well, what if you're doing the guidance system? You're trying to dock a rocket with the space station. Well, relative to the Earth, relative to space, the rocket is a very small. The size and the shape of the rocket is extremely small and insignificant relative to the Earth and to space. And so that's an example where we can use these concepts to do work, to do very real work. Okay, so first let's talk about forces. What is a force? Well, a force is defined by the following. It's defined by its point of application, which ironically we're not going to talk about here in Chapter 2, but we will consider it in future chapters. And it's defined by its magnitude, and lastly by its direction. And direction kind of has two components to it. It has a line of action and it has a sense. Consider a vertical force. Okay, the line of action is vertical, it's up, down, right? But the sense is whether it's up or whether it's down. A vertical force could be up or it could be down, you don't know. The sense gives you the direction of it. Okay, combining forces. So experimental evidence has shown us that two forces can be replaced by a single resultant force using parallelograms. Okay, so what does this mean? Well, you come here. You have this force P and this force Q. You'll notice that it's a force in a direction and a force in a different direction, different force in a different direction. Well, if you draw a parallelogram with these two things, notice is parallel to Q and this is parallel to P, then you put the resultant force here, this R. This particle can be feeling, you can say it's feeling these two forces, or you could say it feels this one single force. And as far as the particle is concerned, it knows no better for it. It's the same effect on the particle. Now, these things, using the parallelogram laws, it follows the law of linear algebra, not scalar algebra. So 2 plus 2 doesn't always equal 4. What do I mean by that? Well, if you have, say, 2 pounds pushing up and 2 pounds pushing to the right, you don't have a total of 4 pounds pushing on this object, but you follow the linear algebra laws to find the magnitude that would be pushing it up and to the right. Okay, and for this class, and I think in general, vectors are going to be indicated in bold. So you'll have in print, it'll be capital, a bold P, or in writing with the arrow on the top of it, P with the arrow across the top again. Anywhere in text, you'll find it like this, but we'll do it like this when we're doing it by hand. Okay, an extremely important video.
Flight 209er, you are cleared for takeoff.
Roger. Huh?
LA departure frequency 123.9er.
Roger. Huh? Request vector. Over. What?
Flight 209er, clear for vector 324.
We have clearance, Clarence. Roger, Roger. What's our vector, Victor?
Howard radio clearance, over.
That's Clarence, over. Over.
Roger.
Huh?
Roger, over.
What? Huh?
Who?
What's your vector, Victor? Forces are vector quantities, so let's talk vectors. So first, let's talk some definitions. Okay, a vector, what is a vector? It is a parameter possessing magnitude and direction, which adds according to the parallelogram law. So some examples of vectors: displacements, velocities, accelerations, right? Magnitudes and directions. Versus a scalar parameter possesses magnitude but not direction. So examples of of scalars are mass, volume, temperature, speed. Look at velocity, for example. The velocity tells you the direction and the magnitude, right? That's what a vector is. It's a magnitude and a direction. Well, the magnitude of the velocity vector is speed. So speed is the scalar, and the velocity has the additional information of the direction. Okay, a little more vector stuff. A vector can be classified in one of three ways. You have a fixed or a bound vector, and they have well-defined points of application, and you can't change those without affecting the analysis. Free vectors may be freely moved in space without changing their changing their effect on the analysis. And lastly, sliding vectors may be applied anywhere along their line of action without affecting the analysis. Okay, for two vectors to be equal, what does that mean? Well, it means they have the same magnitude and the same direction. Now, if a vector is the negative of another vector, it means it has the same magnitude and the opposite direction. Okay, let's talk a little bit of vector math, specifically addition. So vector addition follows a trapezoidal rule, which we just showed. Vector addition is commutative. So what does that mean? It means that the order doesn't matter. P plus Q or Q plus P, it's fine. Or P minus Q or P plus minus Q, it's all the same thing. It's vector addition is associative. So P plus Q plus S is, you can do it in different orders. You can add the P and the Q together and then add the S, or you can add the P to the sum of the other ones, so it doesn't matter. And it follows a polygon rule. Vectors add tip to tail, as many as you want. So say you have 27 vectors, right? So you can go from the tail to the tip, and then the next one starts at the tip with its tail and on to the tip and so on. And then when you're all done, you just start from the tail of the first one to the tip of the last one, and that's your new vector. That's a polygon rule. Okay, vector-ish multiplication. Okay, why do I throw in the ish? Well, because true vector multiplication is actually quite complicated, and we're not going to do it yet. But a vector can be multiplied by a scalar, and it is really simple. Okay, so let's look at the example P, the vector P. So P plus P is equal to 2P. Okay, I know that you don't think that that's anything special, but it actually is. What does that mean? It means that any scalar times a vector, it changes the magnitude by that scalar, and it keeps the direction. This is huge. This is going to be the basis for much of what we do in this class, that you can multiply any vector times a scalar, and you will maintain the direction of the vector, you'll just change its magnitude. Okay, resultant of multiple concurrent forces. Okay, for coplanar forces acting on a particle, remember coplanar, all forces can be replaced with a single resultant force with identical effect. Okay. So what is that saying? If you have 10 forces, you can replace, if there's 10 forces acting on this particle, you can replace those 10 forces with one special vector that has the exact same effect on that particle. This is the basis for moving forward and makes our math much, much easier. And this is extremely important. So we can go from having many, many different forces, many different vectors, and we can replace them with a single force vector and have the same effect. Okay, along those lines, often we want to rewrite a single force as multiple forces. It's called resolving into components. Okay, why in the world would we do that? We just talked about how we can take a bunch of forces and write them as a single force. Why would we want to go backwards? Well, say addition, subtraction, various other things. Sometimes you want to break things up into, say, the portion of the force that, consider a door. You're trying to open a door, so you're pushing on the door. Well, a portion of that force wants to open the door. Maybe a portion of that force wants to twist the door, which isn't going to happen. Or a portion of the force wants to, say, push the door into the wall, again, which isn't going to happen. And so you can break up the forces into the portions of it, the parts of it that you're concerned about. So really, there's unlimited ways to resolve these forces, but some of them make more sense than others. You know, obviously, considering, so chapter 8, we're going to talk about friction. We're going to talk about forces, you know, on a block, say on a sliding, on an incline. Well, maybe it would make sense to talk about, to break up the forces into the portion perpendicular to the incline and the portion parallel to the incline, right? There's all sorts of different ways to resolve the forces. You could do it all sorts of obnoxious ways, but it's really, some of them make a lot more sense than others. In order to do that, we're going to go back to a quick review of law of sines and law of cosines. So I'm hoping this is a review, not the first time you've seen this, and I'm not going to spend a lot of time on this, but Law of sines. What is the law of sines? Well, the law of sines says that the sine of the angle A over the magnitude of this of its opposite side is equal to the sine of this angle over the magnitude of this is equal to the sine of this angle over the magnitude of that. Or you can flip it all on its head and then this magnitude over the sine and so on. That's the law of sines. So when you know, say, a lot of times we'll know, say, this angle and maybe two distances. Well, you can figure out if you know this angle and this distance and this distance, you can then figure out what this angle is and so on. Okay, law of cosines. Law of cosines, hopefully this looks really similar. If you ignore this over, you have a squared equals b squared plus c squared. Nice Pythagorean theorem. Well, but the Pythagorean theorem is only good for a right triangle, right? It's only good for when the theta is equal to 90 degrees. Well, the law of cosines is how we deal with the theta not equal to 90 degrees. And so we have a squared is b squared plus c squared plus the portion of it that changes based on the angle being not 90 degrees. Again, law of sines and law of cosines, I'm going to rely on you either remembering it or going back and looking over this and spending a little bit of time on your own. I'm not going to spend a lot of time on it, but we will use it throughout, especially when we're doing these vector decompositions. Now this last thing is a unit vector, and this is one where I'm not as sure it is something that you're familiar with, and so we're going to spend just a minute on it here. A unit vector, we're going to call it lambda, is a vector with a magnitude of 1 in a given direction. Okay, the whole reason a unit vector exists is to give you a direction. For those of you who took MATLAB or different classes around here, you'll notice there's two numbers that are kind of special, kind of convenient numbers to deal with. 0 is one of them. What's special about 0? Well, you can add anything to it, and you know what you're going to get. You know the answer that you're going to get. You're going to get whatever you added to it. Well, the other one is 1. So what's special about 1? You can multiply it by anything, and you're going to get that value that you multiplied it by. Well, so why does that matter with the unit vector? Again, remember, we just talked about this. We can multiply a scalar times a vector, and you'll change the magnitude of that vector, but you won't change the direction. Well, this unit vector lambda gives you the direction, and given that it has a magnitude of 1, it is defined as the vector that has a magnitude of 1 in a given direction. Given that, then you can go through and you can multiply it by some magnitude to change the magnitude, but you know the direction. So this is going to be a hugely important part of this class, is understanding these unit vectors, and we're going to use them over and over and over. Okay, rectangular components are the real way. So why do I say the real way? So the book, you're going to go through, and some of the first homework assignments, you're going to need to go through and break up the forces using the law of sines, law of cosines, and whatnot. But the way that you'll end up doing it, more than likely, this is the only way I've ever seen it done in industry, is that you break up forces into x, y, and eventually the z components of the force. Now, often left, right, and up, down, would make the most sense, right? We usually define x as horizontal and y as vertical. But there's plenty of times when it's not as obvious, right? Say you're in outer space. What is horizontal? What is vertical? Who knows, right? So, but you still pick an axis and perpendicular axes of x and y. Now, so say you have this vector f. This vector f is the x component of it in the I direction, and the y component of it in the j direction, where I and j are unit vectors in the direction of x and y respectively. We talked about unit vectors. You guys are already familiar with probably 3 unit vectors that we use all the time, I, j, and k. And they are, what is a unit vector? It has a direction and a magnitude of 1. That's what I is. It has a direction in the x direction and a magnitude of 1, and so on. So what we're saying is that you can express this f vector as the x component of it in the x direction and the y component of it in the y direction. And then you can start to define what these are. So f in the x direction is equal to f cosine theta. F in the y direction is equal to f sine theta. I'll show you an example of this. So consider you have some axis. You have the x, y axis. Well, and then in that, you have some force F at some angle theta. Okay, so that force F has a component along the x direction, we'll call that Fx, and it has a component along the y direction, we'll call it Fy. Well, if you look at what that is, what do you have? You have cosine. Cosine of theta is adjacent over hypotenuse, right? So that's Fx over F. So you can solve that for f of x. So Fx is equal to F cosine of theta, right? And the same deal with sine of theta. Sine of theta is Fy over F. It's opposite over hypotenuse. So Fy is equal to F sine theta. And then lastly, you can figure out the tangent of theta is opposite over of adjacent, so that's fy over fx. And so when we talk about fx being f cosine theta and fy being f sine theta, and then as I said, tangent theta can also be found. That's where that comes from through the trig. Okay, why would you do it this way? Well, because quite frankly, it's the way it's done. Because after you do this, you can just add up all the x components and all the y components, and then later we add the z components, all those, and you're good to go. So let's consider a vector r. This r, you have multiple forces, f1, f2, f3, and so on. Well, there's a resultant vector. We talked about that you can have one resultant vector that is the equivalent of all these other vectors. Well, if f1 plus f2 plus f3 and so on, right? The r is the addition of, or the sum of all these vectors. Well, and we can also write r as the x component of it times I plus the y component times j plus the z component times k. Well, how do we figure out what the x, y, and z components are? Yeah, it's really easy. This is why we break it into x, y, z components. The x component is just you add up all the x portions of the f. So the f of x1, f of x2, and so on. The y components, you add up all the y, and the z components, you add up all the z, and then you're good to go. So just through one, you can, once you break up all these different things, and this is how it's done in industry, you'll break up, say you have 10, 15, 20 different forces, you figure out all the x forces, all the y forces, and all the z forces, you add them all up, and that's your new x, y, and z force. And again, as a editorial note, this is how I've done it in industry. This is the only way I've seen it done in industry. I've never seen it done with the law of sines and cosines. Equilibrium, the big nothing. I'm just a big nothing. There's a video that my kids would watch, math, and the zero would come in and say, I'm just a big nothing. And that's what we're talking about with equilibrium. When the resultant of all forces acting on a particle is zero, it is in equilibrium. Okay. So if you have only two forces, this actually is really easy to deal with, right? If you have two forces, they must be equal and opposite. So if you have a force up and to the right of, say, 10 pounds, the only way it's not going to move is if you have a force down and to the left of 10 pounds. Now, if you have more than two forces, it's not always as obvious. And so you have to sum up the forces to determine the resultant. And specifically, you have to sum up the forces at x, and they have to be equal to 0. Some of your forces in y must be 0, and some of your forces in z must be 0. If that's the case, right, if all your forces add up to be 0, then it is in equilibrium, and Newton's first law kicks in, which means that there's some of the forces is 0, so nothing happens. Kind of boring. To figure out these problems, we're going to be using a free body diagram. So let's talk about free body diagrams. First, let's talk about space diagrams. What do we have space diagrams? Well, a space diagram is a sketch showing the physical conditions of the problem. This is the problem that you're going to get in the book. You know, that you're going to get a homework assignment, and it's going to look like this, right? So here you have this truck, and this is load, and there's these two guys pulling on these cables through pulleys to try to lift up this load. Okay, so that's a space diagram. It's showing what's happening. Well, a free body diagram, we're going to choose a quote-unquote significant particle. So we're going to pick something and isolate that and determine, you know, what do we care about? And we're going to look at that particle and show all the forces acting on it. So we're going to look at point A. So you notice we didn't pick this block, we picked point A. At point A, that block is pulling down with a certain amount of force. There's a tension up in this direction with a certain, you know, in certain direction, certain magnitude, because it's a force vector. There's a tension in this direction, certain magnitude. And these tensions, this is the free body diagram. At point A, you have a force here, and a force here, right? Now, you'll notice that these people over here, you don't have a force turning around and coming back down here. You don't have a force turning around and coming back down here. You cut this portion through here, and everywhere where you cut through something, you replace it with a force that you cut through. And now these free body diagrams, this is what you're going to need this all throughout. You're going to be tempted early on. You'll probably be able to do a lot of these early homework problems without drawing a free body diagram, and then you'll think, hey, that's not that important. And then I promise you, come later in this chapter 4, chapter 5, chapter 6, you're going to get bit by that. Please get in the habit now of doing free body diagrams so that you will be able to use those later on. 3D. Now, sadly, that animation probably took me about an hour. So let's watch it again. Dun dun dun. 3D. Okay. When we go into the third dimension, we're going to add the third dimension, and basically nothing changes. Okay. All the things are still true, but now we have an additional third dimension. Okay. So if you know the angles between the forces and axes, resolving forces is easy. Okay, so we want to talk about the f of x, fy, fc. Now remember before we talked f of x is f cosine theta and fy is f sine theta. Well, now we're going to define theta a little bit differently. You'll notice that these say theta x, theta y, theta z. Well, what are those? Okay, so we're saying that the x component of this force, so you have this force in 3 dimensions, right? A portion of that is along the x-axis. Well, the x component of the force is f times cosine theta x. That theta x is in the plane between this vector and this vector. So it's one of those things that it's true and it's nice to know, but it's not overly helpful because generally speaking, you're not going to have that angle. And it's true for fy and fc. They're all f cosine theta y, f cosine theta z. So these things are absolutely true, but you generally don't have this angle. You'd maybe know from here in this xz plane what it is to the projection, and that's not the same thing. Okay, also these angles, these theta x, y, and z, are not completely independent. So once 2 of them are defined, the third is actually also defined by cosine squared of theta x plus cosine squared theta y plus cosine squared theta z is equal to 1. And that's because really you only have 2 independent angles. The third is just breaking down the second angle into components. Okay, so here's a little trick. I say a little trick, but this is the basis for much of what we're going to do. We're going to come back and do this over and over. We'll do this in class. This is one of those things that is very important that we understand how to do this. In order to solve a common problem, okay, when a force is defined by its magnitude in 2 known points along its line of action, okay, an example of this is a rope. Picture a rope. You have a rope tied between, say, 2 points. A rope isn't capable of pulling this point in this direction over here. It can only pull it towards in the direction of the rope, right? So you know the direction that it's going, you just don't necessarily know the magnitude that it's going. So we want to define the force vector F with the following steps. So we want to define that there's some force vector in this rope, say going from here to here. Well, how do we do that? Okay, first step, define D as a vector between the 2 points. So there's a point here, there's a point here. We're going to define D as this whole vector, okay? Now, how do we do that? Well, it's simply x2 minus x1, y2 minus y1, z2 minus z1, right? That's the x component, the y component, and z component. And then what we're going to do, we're going to calculate the magnitude of D. So the magnitude of D is, we're just going to call D, right? And it's the sum of the squares. It's the square of the sum of the squares, right? So dx squared plus dy squared plus dz squared quantity squared, square root, sorry. So the magnitude of the D. So why do we want to know that? Because we're trying to find the unit vector in the direction of D. So lambda is what? We already talked about this. Lambda is a unit vector, and it tells you, it gives you a direction, and it has a magnitude of 1. Okay, so D has a magnitude of not just 1, right? This can be anything. It can be 10 feet, it can be 372 feet, it can be 0.01 feet, right? It can be anything. But it has a direction and a magnitude. So we're going to take this vector and we're going to divide by its magnitude, and then the magnitudes will cancel out and we'll just have the direction. So lambda is this vector, so the x component, the y, and the z component in their respective directions divided by the magnitude. Okay, why do we want to do that? Because what's special about D? D is a vector from here to here. Well, that happens to be, and it's not just dumb luck, it's because that's what we're doing, it's in the same direction as the force, right? Again, because cables can't provide forces in anything other than the direction that they're pointing. And so we're going to say that we're going to define our force vector F by the magnitude of the force. That's F, so this is bold and this is not bold. So the force vector is the magnitude of the force times the direction. Remember, because we can multiply, this has a magnitude of 1, but a direction. This has a magnitude, but not a direction, so we can combine these two. And now we have the magnitude of the force and the direction of the force. And this is going to be something we're going to do over and over and over throughout the semester. So please take a moment to understand this, practice it. We'll do examples of this in class as well. Okay, in summary, vectors are awesome, right? They have magnitudes and directions. A force is a vector. That's going to be the one that comes up a lot in the beginning of this semester. Unit vectors have a magnitude of 1 and they have a direction. Please get comfortable with unit vectors. We're always going to call them lambda and the magnitude of 1 and a direction. Vector decomposition. We can express a vector as the sum of its components, right? You can break a vector into separate components. Equilibrium is when the sum of all the forces is equal to 0 and then it doesn't accelerate. Now it might be moving, right? Because remember, Newton's law is just F equals ma, so it's the mass times acceleration. So if it's not accelerating, then it's in equilibrium. And we talked about free body diagrams, and they're hugely important. Please get in the habit of doing good free body diagrams for all your homework problems. And lastly, we expanded it into the third dimension when we talked about the z component of things, which didn't really change anything. It just adds one more thing to keep track of. That is the end of the Chapter 2 lecture. There are plenty of homework problems for this. Please have a look at them, start working on them, and we'll spend time in class looking over them as well.